Okay, so what is 5G really all about? If we look at the top there, we've got a 10x peak data rate, up to 20 gigabits per second. That's extremely fast. If we look in the bottom left corner, we've got 10 times lower latency than 4G. In fact, it's slightly more than that, but it's down to 1 millisecond. And 100 connected devices, 100x connected devices for every unit area. So this is the delta. This is what's expected. So let's just look at some of the reasons for wanting to do this. 100 times the number of connected devices per unit area. Obviously, the Internet of Things, the industrial Internet of Things, is increasing the number of devices. The number of devices we each carry around with us is increasing. And so what you get is this sort of situation where that kind of cyan color, which is showing on the right-hand side, is what sort of performance you'll get from your internet connectivity at 3 in the morning. Cities there, most to the right are Paris, Sydney, Seoul, any kind of large city. So you can surf the net at 3 in the morning and you're perfectly happy, just like you can drive the freeways around here at 3 in the morning and you're perfectly happy. But when you find yourself, as the number of users come on stream, and start taking bits of that bandwidth away, just like the roads, then when it gets to crunch time, like about 6 p.m., you're right at the left-hand side. You've lost half your performance easily, and it's really just down to the number of users. You're not going anywhere on the freeway, and you're not going anywhere with your connectivity. You're out of bandwidth just as much as you're out of lanes on the road. So this is the driver for that 100 times connected devices, and part of why 5G needs to be radically different. Then if we look at the low latency, 1 millisecond, this is clearly an opportunity to provide for robots, at the very least. The millisecond reaction time will be absolutely necessary if robots are to interact with human beings without causing them any damage. You look at places like Japan, they're investing in robots, they're anticipating 5G, precisely because their population is aging so rapidly. And they need to have capability to lift old people out of bed in the morning, for instance. Other places may be looking at using construction working teams, gangs of robots, anything which is remotely dangerous or hard work, or neurosurgery. Robots are extremely good at this. So for this class of application, this really low latency, this very short reaction time is essential. And so you can see big programs that are going on in Europe and North America, like Industry 4.0 and Made in China 2025, where the first expected applications, of course, are industrial robots, industrial Internet of Things, where 5G can boost the productivity significantly. And then I've got up there thin clients. I mean, on the left, we've got this slowing growth in smartphones. But we've become kind of used to the idea that our smartphones are clients which have been getting fatter and fatter. There's a lot of technology in our smartphones. But once you've got a very fast and very high bandwidth infrastructure in place for communication, then the opportunity is there for the pendulum to swing back towards thinner clients. And that a lot of the heavy lifting for the robots and for the end devices can be done somewhere else, as long as you've got that very high performance communication. So on the right, you can see that there is growth expected for robots, and maybe it'll reach, in not too distant future, something like half the smartphone growth. But of course, that's not all electronics. There's a lot of mechanicals to robots, but they will have a lot of sensor technology on board themselves, but it's really that infrastructure that they'll be driving for 5G and for the AI that may be powering them elsewhere. New bandwidth, new subsystems. What we've got there on the left is what we see around us today, masts at regular intervals, maybe every 2 or 5 kilometers, which have a set of antenna at the top and a baseband box at the bottom. Now this infrastructure is going to get reused in 5G with a number of the lower frequencies. 5G is actually a package of different frequencies from sort of 600 or 700 megahertz up to 3.5 gig, which is beyond the frequencies of 4G today, and then massively into the millimeter wave range, say 28 gig. And it's a package of frequencies where you need them all if 5G is going to be able to provide both, say, rural coverage at the same time as urban very high performance. And you can't really pick and choose. You can't just provide one or the other. But the big change is clearly on the right, the millimeter wave and this notion of CRAN. And we'll push into that. But what I should note is that both the masts and what we see on the right are all connected to the internet backbone, and that in turn is connected to data centers somewhere out in the desert in Arizona, Facebook and Google and everybody else. So let's start with the mast below 6 gigahertz. Now we're trying to connect to user equipment and robots, handsets, cars. We have new millimeter wave radio heads, and they are much more deeply embedded in the urban environment than we see with the mast. These are every 200 meters. So every lamp pole is going to be pressed into service as a place to mount a small cell. And this is clearly a significant change in the amount of infrastructure that's going to be required. And the reason is that millimeter wave attenuates very, very quickly. After only about 200 meters, it's just faded away. And so you need this number of units to be able to communicate and keep the coverage and the connectivity. So what you tend to do is you focus the energy that you've got, the limited energy you've got, you focus it into beams, and then you have the responsibility of following moving users with beams. But the beam isn't tracking just one single user, it's flicking around really rapidly between hundreds of users, passing data and maintaining connectivity as those users are moving. So the beams are enabled by large arrays, but the arrays now use very small antenna. The higher frequency millimeter wave allows antennas to be essentially smaller, but it allows us now to create arrays, which is behind how we achieve our beam forming. So this will give us the extremely fast download that we're anticipating, but it's an asymmetric system. We may find that the upload is to the slower frequencies or to the masts in effect. Now, one of the biggest single differences that millimeter wave has compared with every previous generation of 3GPP standards is that these frequencies do not penetrate walls and they do not bend around corners. And so you have become very used to a continuous connectivity and quality of service when you move from the outside to the inside of buildings with 4G and 3G before it. That's not the case. The only way that you're going to be able to maintain that quality of service is if we start to populate the inside of buildings with small cells as well, with line of sight down corridors or inside the space of rooms. And as you can imagine, that represents quite a challenge for the operators to install that amount of infrastructure and for offices who may wonder whether they want to do that. So we'll examine that a little bit more in a minute. Then we get this notion of cloud a radio access network or centralized radio access network. It's been around a long time, but the time is now ripe for 5G. And what it's doing is it's sharing the baseband across all of these thousands of radio heads. When you look at the baseband at the bottom of the tower, it's frequently not very active, quite a lot of dead time, wasted resources. By centralizing the baseband and being able to apply it where the traffic is ideal for the industry. But we can also, I've got my order slightly wrong, so let me just call out then that we've separated our baseband and our antenna by a considerably greater distance than we had with the towers. These are now several kilometers apart. So we need the lowest possible latency communication, which is optical. And these are likely to be Ethernet on optical. So it's any kind of Ethernet mesh or star or point-to-point. Wherever you can build in redundancy and self-healing into the network, that's an advantage. Now, going back to this edge compute, having established it there's one very good reason for putting it inside this box. It's in the urban area. There will be quite a number of edge compute within each urban area to provide services which are very rapid. It goes back to the robot story. We wish to be able to provide services much faster than going down through the internet backbone and out to something in Arizona. There's just too many steps. So for the low latency, we need the edge compute to be very close. Now, once we've established that and we've got the baseband operating, we start to see that we can use AI to improve the performance of the baseband. There is plenty of opportunity to account for different levels of traffic and environments by using AI and the baseband together. But once we've established AI in the Edge Compute Center, then we can think about massive AI in the sense of providing it as a service to all of those robots and cars and potentially thin clients, which now need some AI heavy lifting. So that's maybe an overview of what the new architecture of 5G looks like. So what are the challenges? There's the move to millimeter wave, attenuates quickly, energy concentrated into beam, AI optimized beam steering, highly sensitive RFICs at these frequencies, form factor and cost concerns, and then the move to the centralized radio access network. So these are some of the big challenges. Now, some of the things that we're going to see here is that intelligent system design is for the tough system design problems like 5G. So some of the things that we're going to look at is how to design for these new 5G air interfaces in a single environment across IC, package and board, maximize the air interface power and linearity with mixed signal and our ecosystem of partners, utilize the Photonics solution to speed the fronthaul and the backhaul design, maximize the performance of the C-RAN baseband and edge compute, emulation with TCAM and 5G tester support, and tensilica IP for the baseband and AI. So we'll see that in the slides to come. So let's start with the fronthaul. So as I said, we have this increased separation. We've got thousands of these cells, all of which need some kind of optical transceivers into their design. And equally complicated Ethernet will require a lot of Ethernet optical switching technology. So a lot of new design work potentially there, or reuse of existing infrastructure, but either way, a focus will be on optical. So we start out looking at these connections between the baseband and the small cells. And there are very strict timing and frequency and synchronization requirements. And so the protocol stack which we need is eCPRI, which is a telecom standard for fronthaul, which is calling upon Ethernet, which is calling upon GPON2, an optical standard, and then some kind of modulation. So we can fulfill the needs of Ethernet with our Ethernet MAC and SerDes. We particularly provide for the time-sensitive networking. If you have a shared infrastructure for Ethernet in an urban environment and you've got some traffic which is low priority mixed with your high critical priority 5G traffic, then this IP's ability to ensure the time of delivery is essential. Then if we go down into the optical layers, we can use our Photonics solution. Here we are creating a modulation scheme using phase shift keying. And we've got our electronic parts and our photonic parts together. And here in the example, we're creating an electro-absorption modulator as a way to create the phase shift keying. So we result in a classical looking constellation diagram. We can see that the number of bits that we can pass down the optical cable are easily separated and easily understood by the receiver. They've got a nice separation on them. Okay, so this is the Cadence Photonics solution. Our partner, Lumerical, was speaking at DAC about a lot of new interesting features which will enhance our overall capability. And of course, built on the backbone of Virtuoso. So when we can get the gratings and the couplers and the modulators and the waveguides out of Lumerical and into our simulators, then we can have that full system simulation. On the right-hand side, we have recently trademarked Curvicore as our ability in Virtuoso to now do curvilinear physical design, which is essential for waveguides, of course. And so we can end the process by calculating the modal properties of the waveguide, feeding that back into the electro-optical simulation for a post-layout simulation, just as we might do with, say, parasitics with electrical design. Okay, so now let's look at the baseband. So we need the baseband in both the user equipment and in the big shared baseband in the edge compute. What happens is the user equipment is sending out frequent signals saying, pilot signals saying, I'm here, I'm here, I'm here. And at each of these points, the baseband is having to process what is the next best set of communication pathways to maintain the connectivity. And as you can imagine, where you have a very high signal strength, you might be able to use parallel beams to send more data concurrently. But as you get to the edge of the cell, you might find yourself with a weak connection. And the baseband needs to calculate how to bounce one beam off a building, another beam off another building, in a way that can constructively interfere at the user equipment to maintain a higher quality of signal, higher energy at the receiver. And so the baseband is doing a lot of processing with a lot of moving parts. So it will be a rack system, and we've talked about all of that. So let's go on. So what's going on with baseband? If we look at the pink blocks, that's our tensilica DSPs, and they are doing these baseband calculations. And one of the first actions they have to take is taking a stream of bits coming out of your Facebook page in Arizona and convert them into something which can go over this air gap. And so we've got this kind of lookup table going on where we take a subsection of the stream of bits and convert it into a phase and an amplitude. And that's what we pass over the air gap. And then the baseband on the other side just does the reverse, the decode of that, and converts that back to a stream of bits. So that's really what baseband is fundamentally doing. It's creating what's referred to as I and Q. So the constellation diagram is split into the two axes of I and Q, which enable a phase difference to be utilized across the air gap. So it's possible that the AI is going to provide this kind of learning about where each of these radio heads is located. There'll be a different context in terms of buildings around it which you can use for bouncing the beams off. There'll be different levels of traffic at different times of the day. So the system will learn organically about how to best provide quality of service in where the people and the time is a set of moving parameters all of the time. And of course, as I said, we want this massive AI with low latency for the robot and the phone applications as well. Right. So let's look at tensilica DSP for these baseband operations. Previously, with the Connex series, we were only able to get up to a certain data rate. And thereafter, you had to go to multi-core to achieve the data rates needed for 5G. The Connex B10 and B20 are an all-new architecture deliberately designed for 5G performance. And so this is an ideal fit for 5G. And the great thing with our solution is it's got a lot of different options, so users can choose where on their power performance area graph they wish their result to actually come in at. So it's a very flexible solution. So here's an example of the 5G downlink functions. Of course, a gigantic amount of 5G is in software, and there is a lot in that protocol stack, but here we've got the downlink functions mapped into the tensilica DSP. Okay, of course, the AI I keep referring to, our DNA 100 processor, very well suited. Of course, it has its sparse compute engine, so any neural nets, convolutions, and samplings can be mapped to that. And because we aren't processing the non-zero elements of the matrix, and there are a lot of non-zero elements, then we're getting approximately 5x better performance than an equivalent array size of multiply accumulates. So great technology again. And there's more IP. We need to hook all of this together. We have fantastic I/O connectivity, whether it's on a single board or multiple boards. Most of it based on our 56 gigabits per second or 112 gigabits per second SerDes. But whether we're trying to connect networking, storage, or the GPUs, or using C6 for accelerators like the DNA 100, we've got all of the glue logic to put it together at very high speed. So we can get that into the edge compute center as well. So with baseband processing and AI and connectivity, we need to, of course, be able to put it all together. And using new speed bridges, we'll be able to push 5G traffic in and out of a pre-silicon SoC design running in either Protium X1 or Palladium Z1, and start evaluating the software, that gigantic amount of software. Typically, the long pole in the tent in any development is the software. To be able to get that software running quickly, early, very important. Now, Protium X1, as we announced it, is 1 billion gates per rack. Palladium is, 9 billion gates. But Protium scales to 32 racks, so it's got a heck of a lot of capacity. Most of the SoCs for 5G on the digital side, things like digital front end or beamforming ICs or baseband, are typically in the range of 500 million gates to 1.5 billion gates. So they're designs which are well suited to the needs of our emulation and prototyping equipment. Oh, and of course, with all of this IP, we've got to put it together. So we're all aware that Innovus has made some strides with machine learning. And if, as is the case with most of our customers in the 5G infrastructure space particularly, they're moving, it's a surprise. They find these frequencies quite daunting. Their previous business didn't go any higher than 3 gigahertz. Equally, they find things like new advanced process nodes quite daunting. Cadence is here to help. But it's a challenge. So when some of these big new digital 5G designs are being undertaken by a customer on a greenfield site, as that design is being evolved, as new features are being folded in, the learning process as they go is being maintained by Innovus such that the focus of the design can be improved over time. So we've got machine learning inference engines sitting inside Innovus, and we're undergoing training and feeding back the weights as we go. Okay, so we've got all these ICs, all of the big boys like Nokia and Ericsson have got to start putting them together into cabinets, very high-speed board designs. So you need to be able to do things like auto-tune the delay and the phase in these byte lanes. You can see all the little wiggles that have been introduced. You need to have Sigrity there to do the analysis of the electromagnetic effects, the signal integrity, the power integrity. Anything which is a sort of gigabit design running at very high speed needs this sort of analysis capabilities. So if we're going to talk about Cadence's intelligent system design, you can see that we've walked ourselves all the way from the IP to the design of the rack here for the edge compute. Now, let's take an example of one of my most recently announced products with Clarity. So we've got a couple of chips here in that edge compute, and they are connected via a backplane. And this is what's known as a long-reach communication. These communications are traveling through a number of parts. The transmission on the IC, going through the redistribution layer in the package substrate, into the externals of the package, into the traces on the PCB, to connector, backplane, and so on. Every one of these elements is introducing a kind of electromagnetic distortion to the progress of the signal. Every one of these needs to be extracted and folded back into the simulation. Otherwise, our time of communication for this long reach isn't really understood. So this is something that our new system analysis group has been able to work on and provide something which has been very well received. Because what happens is with the hundreds of CPUs, we're able to do this in a single pass. The legacy solutions, which have got a very strong position, you have to break these into individual problems, solve them individually, stitch them all together again. Time-consuming, potential for delay. And even though these solutions have held a strong grip on the market for a very long time, they're under some threat because they're antiquated in that regard. So this is all good news. What are we doing in millimeter wave? Here we can see a handset, and it's got a number of 5G RF units. Ideally, those would contain 4G, 3G, 2G, and so forth. But the initial ones that are being made available by companies like Qualcomm at this point are 5G only, and you need the other chips for the other parts. But you have several of them because your fingers will attenuate the 5G signal. It's that sensitive. In the radio head, we've got these small antenna built into arrays, the massive MIMO as it's called, to enable all the beamforming. And on the flip side, we've got a bunch of RFICs which are driving those antenna. So we've now got a number of elements in close proximity in the RF module which need to be co-designed. Such is the sensitivity at these frequencies that the design of the IC is dependent on the module, and the design of the module is dependent on the IC. So this is why we introduced the Virtuoso RF solution, to enable the co-design between the module and the ICs that go on it, and to deal with a variety of different technologies at the same time, build it all out from a single schematic. And very importantly, to integrate electromagnetic analysis. So we did the deal with National Instruments, where their Axiom EM solver is part of the deal. It's a 2.5D method of moment solver, as well as our existing Sigrity 3D FEM solution. So we've now got a number of alternatives to enable a complete RF module design to be achieved for these very difficult frequencies. So what does it look like? It's something like that. You've got gallium arsenide, gallium nitride, CMOS parts you're trying to integrate together. You're trying to put them onto a package substrate which you're co-designing. You're worried about the inductances of the bond wires or the spiral inductors that you might have embedded in the package substrate. And you need a whole variety of different capabilities to make this work. PDKs for the gas, for the CMOS, package libraries, surface mount device libraries, transmission line libraries, and it takes a lot of parts to make this easy, and that of course is what Virtuoso RF aims to do. Now, the announcement that we made on Monday about the Spector X simulator, fantastic to be able to claim silicon accuracy like Spector APS before it, but at 10x the performance and 5x the capacity. It's a real amazing result, because as the sub-bullet says, or the sub-headline, accuracy you know, speed you need, and everybody needs speed. And so looking back at that Virtuoso RF solution, where Spector is performing a lot of this simulation, it just plugs straight in there. The route to design excellence, as we said right at the beginning. We're providing more horsepower for designers. So let's look at these high data rates that we're trying to achieve. We talked about this getting over the air gap. We talked about this phase and amplitude coding and decoding. If we look at the RF parts that are responsible for getting that over the air gap, what I've drawn there is actually a 4x4 constellation diagram, which is delivering 4 bits for every symbol passed over the air gap. But in reality, 5G is going to go up to 124 QAM, quadrature amplitude modulation, which is a 32x32 constellation diagram. Now, the box represents an energy, and you can't just make the box bigger to fit 32x32 because you'd be burning your battery and your devices very rapidly. So instead, you've got to pack 32x32 into that same energy. And that becomes very difficult because the chances are that these symbols start to jitter and move around, perhaps interfere with each other in ways that mean that the receiving equipment simply can't work out what you're trying to tell it. You can't decode the signal. And so a 32x32 is providing 10 bits of data, a substantial improvement in throughput. We talked about other techniques like the parallel beams, but they all add up as a way to improve the throughput. So classically, one of the problems is the power amplifier. It tends to distort when you run it at the full power range. And we get this compression. So we introduce this digital pre-distortion, a digital correction algorithm, which we add to the compressed signal to give the linear output that we want, that keeps all those constellation points in the right place. If we didn't have the DPD, the actual diagram would crush together, bringing all of the points on top of each other. So this is why we need digital content in our RFICs. It's rising very rapidly, it's decimation, it's clipping, it's linearity. And so we've got, of course, our mixed signal leadership solution, where Spector RF and Virtuoso RF can work together with Excellium and Innovus so that we can do these kind of mixed signal solutions. And of course, we have a great partnership with MathWorks, and so Simulink is able to drive in whole 5G frames at the system level, while we are processing at the transistor level. And this ability, this system design capability, of course, is a win for our customers. Okay, so also just almost a standard slide, but the RF guys are being dragged into advanced nodes. Analog and RF guys do not like advanced nodes. They bring a lot of problems, as called out in the red circles. But the good news is that when you need much more digital content, typically the RFICs can have 80% of the real estate is digital, and not too much of it is left is the RF and the analog. But when you're called upon to support digital advanced processes, then Virtuoso is a great out-of-the-box solution. If you compare a design at 28 nanometers and see what it looks like at 5 nanometers, quite different. There are quite substantial rule changes as you go down the processes, so we get this kind of row-based design, and the Virtuoso advanced node guides our users into ensuring that they get the yield that they're expecting from their foundry by following all the necessary rules. Okay, and just as it were a final call out for clarity again, if we're looking at creating those small cells and we're trying to take our electronics and fit them into a small footprint that we can attach to our lamp poles, then we get these kind of electromagnetic interferences that again we need to worry about. So an easy win for clarity there. So this is a list of Cadence's capabilities for 5G, breaking it down into handset and radio head, baseband and edge and fronthaul. And what you can see is all of the underlined ones are links to solutions on cadence.com. The black ones are sort of standalone tools. And it's amazing how much of it is underlined, because a system problem like this takes our solutions, not our point tools. So whether you're talking about silicon sign-off and verification, or mixed signal, or 3D IC, or low power, advanced node, the solutions that we have can be applied in this difficult problem domain. So summary, it's not actually the summary, but we'll come getting there. It's one of the most high-profile and political technologies our industry has seen. Governments and cities around the globe all see 5G as necessary infrastructure if they're to be successful in the digital economies to come. 4G is out of bandwidth. Long term, there is nowhere else to go than millimeter wave. Unlike previous generations, millimeter wave is a whole new teleco architecture, and that will take even more time to build out than, say, 4G. 5G and users can't rely on millimeter wave alone. The standard covers multiple frequencies to provide both coverage and performance. AI may be arriving just in time to overcome the limitations that we've always known about millimeter wave. Massive AI may be available on tap through high-speed 5G infrastructure. Higher speed 5G could swing the pendulum back to thinner clients. Millimeter wave has logistical as well as technical hurdles in Western democracies, and indoor connectivity could be a 5G versus Wi-Fi 6 battleground. So there we have it, 5G intelligent system design. We talked about designing the new air interfaces across the IC, the package and the board. We talked about maximizing the interface power and linearity. We talked about photonics for fronthaul and backhaul. We talked about the building blocks for CRAN, baseband and edge computing. We talked about powerful emulation and 5G tester support. We talked about Tensilica for baseband and AI. And that, I believe, is it.